Hello everyone. Today I will talk about Similarity Fairness 3D plot inspired by the sentence, similar subjects must be treated similarly. My name is Jose Francisco Sarray Villamizar. I am a senior data scientist and this presentation won't last more than 20 minutes. So this is the outline. First, I will give you the motivation for giving this talk. After, I will introduce the similarity fairness definition, and at the end I will show you a practical example how you can use Kafkanator API to assess similarity fairness in a specific problem. So the motivation is that artificial intelligence and algorithm adoption are shaping the future by deciding by ourselves. The debate is on the table. How much of the decisions that shape our life should be delegated to machine learning or statistical models? Are these decisions being fair? Similarity fairness is one of many ways to measure fairness in an ML model. This term was first used in Fairness Through Awareness paper from Work et al. I got inspired from this paper to show a way of inspecting the quality of your machine learning predictive model. Continuing with the motivation, let's imagine the dataset that is in the right part of this slide. Let's imagine that this is the two examples, but let's imagine the big dataset that consists on men and women, and it's a dataset about default payment prediction, and so we have here the prediction if someone will pay or not. So for such a dataset, we will have a sensitive attribute that in this case will be the gender, and the prediction or target column that will be 0 or 1. Then this type of datasets with a sensitive attribute column can be split in a subpopulation of two big subpopulations of men and women. And let's imagine we gather different couples of this type when one comes from different subpopulations and they are very similar between them. For example, these two subjects only differ in 2 years of age and in 100 euros in monthly income. And even with this similarity, the system tagged with 0 and one with 0 and the other with 1, introducing potential unfairness. So my take-home message is, if you have tested your ML predictive model for this feature, any two different subjects belonging to different subpopulations but similar are having the same output. If not, can you explain why? This slide is only to show where similarity fairness is belongs to in the big landscape of fairness measures. There is group fairness, when we have the classical group fairness metrics, demographic parity, equal opportunity, equalized odds, etc. And on individual fairness, we have the counterfactual that I will make a video later for explaining it, and also we have similarity fairness. So the mathematical definition is that, let's suppose you have a function m from a set of individuals p to predictions p. So there is a distance measures that satisfy the three axioms or definitions for distance measures: the commutative, that the distance is 0 only if the element is the same, and the triangle inequality. We have a distance measure that satisfies this, is we call D, and a mapping M from the rows of the table, for example, to a prediction 0 or 1, or a float between 0 or 1, and this mapping will satisfy the Didi-Lipschitz property if for all x and y belonging to our table we have this property, that the distance between predictions for every x, y we take are less than or equal to the distance measure that we are proposing. In English, another way to put it is that similar subjects must be treated similarly. If we have a predictor that is sending each element of a data table into a space of predictions, we should expect that if we want that model to be similar, that satisfies similarity fairness, the distance between the predictions must not be bigger than the distance in the data table that we define in the data table. So this is another slide to try to make clear what I said before. So we have, imagine we have this data set. We take for every 2 pairs of subjects, we make this. We have the data frame. We have our distance measure, from which we build this distance matrix, and this will give us an arrangement very similar to this. You can check it later, but it's more or less this. The 1 and 2 are for example, if we take 1, we see that the 1 and 2 are very close compared to 3, 4, and 5. The 5 is the most distance to 1, and so on. So if we have such an arrangement here, and we have a predictive model, the predictions of the model must not be will not alterate the distances too much of our in our data table. So this is what we are expecting if we want our model to be satisfying the similarity fairness constraint, and if not, it will have something very chaotic like this. This won't comply. So now I will show with the very famous Compass dataset, I will show you how you can use Kafkanator to assess similarity fairness in a model. So I will take a very famous example is Compass. Compass stands for Correctional Offender Management Profiling for Alternative Sanctions. It was a statistical model used in 2016 and before in order to apply or input a probability of recidivism to a population of people that are in jail. So we will have a data set when the sensitive attribute is the race. We have Caucasian, no Caucasian, and the target is the risk of recidivism. He will do something bad again and he will get into jail again. It's a prediction of the future, what will happen. So this dataset exists, it's available online, and there was an independent newspaper that is called ProPublica that they made a research on this statistical model, and they found that it was biased against not Caucasians. You can check the details of their conclusions here. So it's a very important model that should make us aware of the consequences of going more than we should on machine learning and applying it everywhere. So I will apply this, what we saw in the previous slides, on this model and check if it respects the similarity fairness constraint. So first, I propose this plot. Is the similar treatment 3D plot, and it did come with the API of kafkanator.org that I invite you to download. So this plot, what is this plot? This plot depicts a 3D scatter plot of x, y, z coordinates, such that the x, y are the row IDs of individuals. The x are in one subpopulation and the y in another subpopulation. Z is the distance between x and y, and we have here all only the points where the predictions on every the predictions of some model on every subject on each subpopulations are different. So we have here satisfy this. Every point here satisfy that the probability or the prediction of X was different than the prediction of Y, and as a consequence, the closest the points are to the plane Z equals 0, the more likely they have unfair treatment, and these points are in a darker red. This plot comes with a tooltip that will indicate which XY are you signaling, and it will show in a very ergonomic way the two offending pairs, the two offending subjects, in order that the domain expert analyze them. And no final conclusion can be achieved without field expert inspection. This is the input of the function. It comes with parameters, the data frame, the sensitive attribute column name, the two values of the sensitive column name, the amount of rows you want to check in the dataset. This is because, as you can see, this is a Cartesian product. So if you put a 1 million rows dataset, it will explode the time. So you have to be progressive, doing this progressive, because it's a Cartesian explosion. And the similarity distance that we will use by default is Gower. The idea is that you can put a customized similarity distance, but it comes with Gower distance. This distance is very famous in data science because it allows you to establish a similarity between two subjects having different values, numerical and categorical. So it fits well our needs. And it will return a dashboard that I will show you in live. So let's see our live notebook. So this is the Python notebook. It comes with the API that you can download in kafkanator.org, and here you start to execute it. Here is the URL of the Compass dataset. You download here. You process here this to take out duplicates, and at the end it will give you this number of rows that it respects what it said in the ProPublica paper. They say at the end they have this number of rows and they work with this number of rows. And once we have this, I inspect the data set. I make some data cleaning. I drop some columns that I consider are useless for our purpose. I transfer into categorical columns, some columns, and here I perform the call to similar subjects dashboard. I will repeat, of course, to show you in live, but this was already done before. So because this dataset originally has 54,000 rows, and I am erasing the duplicates, so I will take some time. So while this is working, let's see let's continue. So I call the similar subject dashboard that returns a dash application. I execute the dash application here, and we have our pretty similar subjects plot. that we can see here. So our main concern is these are the bottom dots, and because those dots imply that there was a Caucasian compared with a no Caucasian that are very similar, and they got different classifications from Compass. So it's very important that an expert go and check and see what is happening and why this is happening, because it's something that should attract our attention, that two very similar subjects are having different predictions. So this one is the here we can see in the top 10 is the 370 and 405. 347 and 405. And as I told you, they come with the tooltip. This is the tooltip. They show you the similarity and the rows IDs on Caucasian 347 and no Caucasian 37, or the opposite, but it's not very important that. So this one was the one I want to inspect. There is the first that is very similar, and although this, they have a different prediction. So we have it here, and indeed we see that the only difference is that they are in a different decile. The rest is almost the same. They differ because one is Caucasian and the other is not Caucasian, and they got different probabilities of reincidence. And the no Caucasian is tagged as with high probability of recidivate. Although it is very similar to a Caucasian, it only differs on this attribute. So it's the type of things, I am not an expert on this data set, but an expert should inspect this and see if this is fair or not fair. But the plot make us easy the task of comparing and check. So it was a pleasure to share with you this plot, and the conclusion is that be careful when handling machine learning models. Always make a QA step checking for fairness in your model, especially before production. And another important conclusion is that applying machine learning models in the justice system at this moment is very premature. Some comments about the dataset. I only want to show a graphical output of similarity fairness analysis. The dataset has been widely analyzed, and ProPublica published its analysis and preprocessing here. I perform my analysis on this number of rows, but I am the only one working on this, so I don't have any research partner at the moment. If you detect any errors, kindly report them to here. And you can reach me on this email for more information. The bibliography. Thanks for the authors for doing this. And subscribe to my YouTube channel. And this is my email if you want to contact me. Thank you. Bye bye.